Hi, everyone, and good morning, good evening, good afternoon, wherever you are. Welcome back to the annual Cementing Leaders Forum. I'm Jordan Trosclair, Global Sales Manager for Cementing. I'm your moderator this week. We've had some really great sessions. This is day 3 of 4. Our sessions so far have been around digital topics such as Halliburton 4.0, virtual remote operations, IDOS well programs. ISIM 7.0 was a hot topic. We've had a lot of great Q&A. We will have a live Q&A at the end of every session, so please, in the chatter, please send your questions at any time, and we'll do that at the end. We've also had sessions, our second sessions on each day were on sustainability, as well as design considerations for sustainable barriers. It's been very engaging. We've had a lot of great questions. I encourage you to keep up with active participation. It's how we get better. And we thank you very much for your time today, and we're excited to get started. So without further ado, I'm going to hand it over to Simon Turton. We have a jam-packed day on sustained casing pressure. So Simon, I'm handing over to you.
Depending upon where you are in the world, good morning, good afternoon, and good evening, ladies and gentlemen, and welcome to day 3 of our Cementing Leaders Forum. The first presentation this morning is a holistic approach to understanding and eliminating sustained casing pressure. This presentation will cover an industry definition of sustained casing pressure, an introduction into published regulations and guidelines, how sustained casing pressure occurs and when, calculations to predict hydrocarbon flow through unset cement, and tailored and technical solutions for successful cement placement across reservoirs that may produce flow. So how does our industry define sustained casing pressure? Sustained casing pressure is excessive casing pressure in wells that persistently rebuilds after bleed down. It is defined as a pressure in any well annulus that is measurable at the wellhead and rebuilds after bleed down, not caused solely by temperature fluctuations or imposed by the operator. Sustained casing pressure is caused by hydrocarbon migration from a high-pressured subsurface formation through a leaking cement sheath in one or more of the well's casing annuli. Gas leakage, leading to sustained casing pressure, may occur through the pore cement bond between the casing and the formation, the packer, and or the casing itself. All safety regulators require sustained casing pressure elimination. However, test data analysis is mostly qualitative and limited to arbitrary criteria, thereby lacking consensus. Today's presentation will provide insight into industry criteria for identification of sustained casing pressure and acceptable limits. So, should operators be concerned about sustained casing pressure? I think so, and here's why. When sustained casing pressure is observed in a well, it's evidence of failure in one of the well barrier elements. Once the sustained casing pressure is confirmed, the well is potentially not in compliance with most operators' barrier policies. Okay, so what should you do next? The well can be killed and secured immediately, or a risk evaluation can be performed and the well allowed to operate for a limited period of time under close surveillance until the barrier integrity has been restored. The main challenge here is how to identify this window in which it is safe to keep production from the well flowing. The answer to this question varies from place to place as legislation, operators' standards, and environmental conditions all play a role in this matter. However, the ultimate goal of well integrity is to prevent well control situations, uncontrolled release of hydrocarbons to surface. It all comes down to establishing what stops the sustained casing pressure affected wells from further barrier failure that leads to a well control situation. This is mostly about the integrity of the secondary barrier, such as the wellhead, containing the leak and the severity of the leak itself. Sustained casing pressure can affect more than 30% of all global oil and gas wells. A study was performed during the period of 2009 to 2015, a period of 6 years, and the study concluded that well integrity has cost operators over 75 billion US dollars. A study in 1998 of Gulf of Mexico producing wells showed that 11,498 casing strings exhibited casing pressure out of 8,122 wells investigated. A study in 2015 in the Middle East revealed that there were 50% of the wells exhibited annular integrity issues, with 15% of these classified as critical. So, are there any industry published regulations and guidelines that define annular leakage rates and pressures associated with sustained casing pressure? Yes, there are, and over the next few slides, we will look at the American Petroleum Institute, the US Minerals Management, and NORSOC sustained casing pressure guidance, for which these are just a few of the published documents available to our industry. API, the American Petroleum Institute Recommended Practice 14B, identifies an acceptable leakage rate for a closed subsurface safety valve. This leakage rate should be no more than 15 standard cubic foot a minute for gas, and no more than 0.11 gallons per minute for a liquid hydrocarbon. Additionally, if H2S is present, then permissible concentrations are no higher than 100 parts per million. The API also published a document, American Petroleum Institute Standard 90, for offshore wells that goes into more detail of how to establish an acceptable sustained casing pressure risk level using two parameters. The first is, if any annular pressure greater than 100 psi can be bled to zero, then the leak rate is considered small and the annular barriers can be classified as effective. The second is a procedure to calculate the maximum allowable wellhead operating pressure, or MAWOP. The maximum allowable wellhead operating pressure is based on the minimum internal yield pressure, the MIYP, of the one being investigated and the next outer one, as well as the minimum collapse pressure, or MCP, for the inner tubular being investigated. The maximum allowable wellhead operating pressure for an annulus is expected to be less than 50% of the minimum internal yield pressure of the casing string being evaluated, or 80% of the minimum internal yield pressure of the next outer casing, or 75% of the minimum collapse pressure of the inner tubular pipe body. In case of the outermost pressure containing casing, the maximum allowable wellhead operating pressure can't exceed 30% of its minimum internal yield pressure. The API went on and expanded Guideline 90 to Guideline 90 Part 2, and this presents two alternative calculations for sustained casing pressure. The first of these is to use the default designation method, or DDM, which can be applied to most offshore wells and states the maximum allowable wellhead operating pressure for the well under investigation is 100 psi for the outermost annulus and 200 psi for all other annuli. The second calculation is applicable when a cemented casing string has known wear, erosion, or is operating under high temperatures. The calculation of minimum internal yield pressure and minimum collapse pressure involves an explicit derating method, or EDM, where a reduction in wall thickness and hence material properties is applied. The US Mineral Management Service, or also known as the MMS, impose diagnostic testing in all wells that exhibit sustained casing pressure. The result from this diagnostic testing will determine the extent of sustained casing pressure and whether a waiver will be granted to allow continued production or whether greater steps need to be taken to eliminate the sustained casing pressure. The regulatory authority in Norway, NORSOK, published a document called D10 that states all accessible annuli should have designated minimum and maximum operational pressure limits, and they should always be monitored. So, having cemented a casing spring, how long does it take for sustained casing pressure to appear? There are two timelines for sustained casing pressure to occur: short-term and long-term. Short-term is when hydrocarbon flows through the unset cement and is usually visible within a day or two post-primary cement job. Long-term is when hydrocarbon flows through mud channels left behind in the cemented annulus and is usually visible a couple of months post-primary cement job. Short-term sustained casing pressure is due to the potential loss of overbalanced pressure caused by the development of cement static gel strength, the cement transition time, and hydration volume reductions. In contrast, long-term sustained casing pressure is due to the cement's plastic state shrinkage. This shrinkage weakens the bond between the cement and mud filter cake, creating a micro crack, which in turn provides a conduit for hydrocarbon migration. This shows the need for excellent mud displacement and filter cake removal practices to prepare the annulus for primary cement. It is usually observed that hydrocarbon flow volumes start off small, however increase over time as the filter cake is dehydrated. So why is sustained casing pressure a problem, and what possible consequences can occur? Sustained casing pressure by unwanted hydrocarbon flow in the annulus can contaminate aquifers used for residential consumption, as well as present the operator with potential well control issues. At a time when environmental improvements are a key agenda item for us all, sustained casing pressure can lead to unwanted release of gas, often referred to as fugitive emissions. The industry is well aware of the environmental impact of carbon dioxide release. However, natural gas, or methane, also has a negative effect on the environment, some 60 times worse than that of carbon dioxide. It is estimated that methane is the single largest source of unintended greenhouse gas emissions from oil and gas production. Now we will look at the main causes of annular hydrocarbon migration. Microannular flow can be induced by the following: damaging the annular cement by early drill out of the shoe track, or by pressure testing the casing at the wrong time. Poor mud and filter cake removal, resulting in low fluid displacement efficiency and poor cement bond. Weak zones and unconsolidated formations can also play a part by robbing the annulus of its required cement volume. Steps to prevent inducing a mechanism for sustained casing pressure include: avoid drilling out shoe tracks and liner tops until the cement is fully set. Pressure testing of tubulars post-cement placement should take place as soon as the top plug lands or the cement is fully set at the real bottom hole static temperature. Additional considerations should include the incorporation of post-set expansion additives in the cement to counteract cement shrinkage, as well as compressible or foam cement solutions. Leading into the next section of this morning's presentation, we will now review why hydrocarbons can migrate through unset cement. Migration can occur due to the loss of hydrostatic pressure exerted on the hydrocarbon-bearing reservoirs as the cement sets. Cement setting occurs in 4 distinct stages that are shown along the top here. Fluid, as when we pump it, the cement gels, it then sets, it then continues to develop compressive strength. The graph on this slide, we have hydrostatic pressure versus time, and it shows the loss of hydrostatic pressure during each of these 4 stages. The overbalance pressure, which we see here, is the difference between full hydrostatic pressure and the reservoir pressure. When the hydrostatic pressure has reduced to the point, due to the cement generating gel strength at the point where it is equal to the reservoir or formation pressure, is called the critical static gel strength of the cement. In this slide, we can see how the hydrostatic pressure loss created by the cement forming static gel strength is calculated. Additionally, the equation for calculating the critical static gel strength is displayed. We see here that the change in hydrostatic pressure is the cement's static gel strength divided by 300, multiplied by the length of the cement column above the zone of interest, divided by the effective annular diameter, which is the OD of the casing being cemented, and the ID of the open hole section. For the critical static gel strength, we just rearrange the equation to have the overbalanced pressure, which is the hydrostatic pressure minus the pore pressure, multiplied by 300, divided by the length of the cement column, and again the effective diameter of the open hole. When considering the displayed graph of time in minutes on the x-axis and static gel strength in pounds per 100 foot squared on the y-axis, 2 crucial periods need to be considered in the cement design to control sustained casing pressure. The first of these is the zero gel time, defined as the time on a static gel strength test from the beginning of the static period to when a cement slurry reaches a gel strength of 100 pounds per 100 foot squared. Secondly, the critical gel strength period, or CGSP, defined by American Petroleum Institute Standard 65 Part 2 as the time between the development of the critical static gel strength and a gel strength of 500 pounds per 100 foot squared. It is during this period that there is potentially unwanted hydrocarbon flow through the unset cement. So tests have shown that when the cement reaches a static gel strength of 500 pounds per 100 foot squared, there is sufficient internal resistance to not allow hydrocarbon flow. So how can we predict hydrocarbon flow and the severity that it presents us with during the cement design phase? To perform this analysis, we need to calculate the reservoir's flow potential factor. Simply put, this is the maximum pressure reduction divided by the overbalance pressure. The maximum pressure reduction is the same formula as we saw earlier to calculate the hydrostatic pressure loss due to static gel strength development in the cement at a gel strength of 500 pounds per 100 foot squared. That gives us the constant of 1.67. The overbalance pressure is the hydrostatic pressure minus the reservoir pore pressure. This calculation results in a dimensionless number that needs to be categorized for slurry and job tailoring to suit the specific condition. There are 3 distinct categories for flow potential factor. The first is minor for flow potential factors from 1 through 4. The second, moderate, for flow potential factors 5 through 7. And the third, severe, for flow potential factors of 8 through 15. A job with a flow potential factor of over 15 would require redesigning, potentially incorporating a multiple stage cementing tool or an effective larger diameter between the open hole and the OD of the casing being cemented. Considering the first category of minor, the cement slurry design should incorporate a fluid loss of less than 50 cc's in 30 minutes. This reduction in fluid loss will limit the maximum pressure reduction due to filtrate losses. Additional design considerations could incorporate applying back pressure, reducing the length of the cement column by incorporating a multi-stage cementing tool with an external annular packer, increasing the mud or slurry density, increasing the effective diameter between the open hole and the OD of the casing string being cemented, and inclusion of a post-set expansion additive into the cement design to counteract any possible cement shrinkage. Now, I'd like to introduce Halliburton's extended range of OBEX compression set packers that can be run in combination with a multi-stage cementing tool to perform primary cementing of a casing in more than one stage. This will reduce the flow potential factor, reducing the likelihood of sustained casing pressure. Additionally, the OBEX compression set annular packers will support second stage cement, reduce hydrostatic pressure on the formation, achieve cement to surface, stop annular flow during primary cementing, eliminating sustained casing pressure. There are three types of OBEX packer available for providing an additional mechanical annular barrier. The first of these is the standard OBEX EcoLock, providing economical, reliable performance. The second is the OBEX ISOLOck, providing operators with a V3 rated liquid barrier for flow insurance. The OBEX ISOLOck will be available initially in 13 3/8 and 9 5/8 sizes. They will have packer element pressure ratings of 4,000 and 6,000 psi respectively. Lastly, the OBEX GasLock annular packer features slips providing operators with a V0 rated gas flow barrier. The OBEX GasLock will be also available in 13 3/8 and 9 5/8 sizes. The bidirectional pressure rating for the 13 3/8 OBEX GasLock will be 5,000 psi. V0 testing is a bidirectional gas test incorporating axial loads with temperature cycling to ensure the tool provides a bubble-tight gas seal. In contrast, V3 is a liquid test incorporating axial loads and temperature cycling. Now let's consider the second category of flow potential factor, or moderate. For this category, we need to design the slurry to have an even tighter fluid loss control, less than 25 cc's in 30 minutes. This reduction in fluid loss further limits the maximum pressure reduction due to filtrate loss and in turn lowers the flow potential factor. Additionally, we need to design the slurry to have a transition time of less than 45 minutes. Less than 30 minutes is common for this flow potential category. Thixotropic cements that, whilst in shear condition, exhibit low gel strengths, however under static conditions gel rapidly, can be considered for use in the moderate category. Halliburton's gas stop additives provides excellent fluid loss control for a moderate design, delays the gel strength development, rapidly gels through the critical transition period, used in wells having moderate gas flow potentials. The incorporation of gas stop additive into the lead slurry allows good transmission of hydrostatic pressure. Cement can also be treated with latex to obtain slurries with excellent wetting properties, low viscosities, and increased resiliency. These properties help increase bonding strength, resulting in tighter annular seal and superior zonal isolation. The latex additive helps provide resistance to attack on the cement sheath by corrosive fluids such as acids. Under high temperature downhole conditions, latex additive also can provide excellent solid suspension properties in high density slurries, and it can also exhibit excellent rheological properties while helping to control slurry segregation. Slurries can be designed with latex additives to function in accordance with Halliburton's gas migration theory, the flow potential factor that we've just seen. Slurries containing latex additive can provide low fluid loss control, delay the static gel time, and shorten transition times. Latex additive can also be used in conjunction with Halliburton's Zone Seal isolation cementing service for foam cement. Halliburton's new IsoGuard cement additive and IsoBond cement system are also excellent new technologies that should be considered for the slurry properties they impart. Please join this afternoon's session as we introduce the newest additions to our flow prevention portfolio. The final category of flow potential factor is severe. In this category, fluid loss control, transition time, multiple stage cementing, and delayed gel strength or thixotropic slurries are insufficient alone to control hydrocarbon migration. For the severe category, we must consider compressible cement systems that compensate by volume change for decrease through filtrate loss. Compressible cement systems include in situ gas generating additives such as Halliburton's Super CBL and foam cement such as Halliburton's Zone Seal isolation process. Recently, Halliburton introduced an additional tailored cementing solution that should be considered when sustained casing pressure is of concern. This solution is Halliburton's Channel Fix cement additive. The Channel Fix cement additive swells and seals any flow paths when exposed to non-aqueous drilling fluid, hydrocarbons, or methane in a supercritical state. Channel Fix additive presents operators with an additional assurance to maintain integrity and dependability of the primary cement annular barrier. Channel Fix is currently being used extensively in our North America land operations, as well as being evaluated to be introduced initially to 8 Eastern Hemisphere locations. That brings us to the end of my presentation this morning on a holistic approach to understanding and eliminating sustained casing pressure. So in closing, I'd like to summarize the main themes to consider when designing to eliminate sustained casing pressure. There are published guidelines with specific guidelines to classify sustained casing pressure, including publications from the American Petroleum Institute, the US Minerals Management Service, and NORSOC D10, just to name a few. We need to understand the source of sustained casing pressure and whether it occurs in a short or long term. Operators' carbon footprints can be reduced by curing sustained casing pressure and fugitive emissions. Application of cementing best practices, CAMPS, which is centralization, annular fluid velocity, mud properties, pipe movement, and spacer design, for the high fluid efficiency and mud filter cape removal in combination with advancements in annular compression set packer tools for an additional annular mechanical barrier. Calculate the flow potential factor and tailor the slurry design using the most appropriate solutions for the category calculated. Additional insurance by incorporating into the cement design of service a secondary barrier with an OBEX compression set packer and a multiple stage cementing tool, gas stop, latex and IsoGuard cement additives for lowered fluid loss and reduced transition times. Channel Fix cement additive for interventionless remediation or a compromised cement sheath. I would like to thank everybody for your time today and hope you found the information presented in this session useful. I will now pass the microphone to our rapid fire presenters. Thank you.
Thank you, Simon, for presenting. Before we start, let me introduce myself. I'm Mohammed Al-Marzouk, Casing Equipment Account Representative for Halliburton. It's an honor to present to you today, and I'll be speaking about the OBX compression set annular casing packers. Let's talk about the basics of why do we perform a multi-stage cement job and what is the history behind them. As we all know, cementing a weak formation and in losses environment are challenging, especially if we want to achieve a good zonal isolation. So one of the solutions to address these challenges is to perform the cement job in 2 stages, which is to reduce the fluid hydrostatic column on the formation and then to be able to cement the cased hole and achieve a proper zonal isolation. Historically, the operator used the inflatable packers to hold the second stage cement slurry, and they've been used successfully. But in some cases, the operator observed sustained casing pressure after performing the 2-stage cement job, which required the operator to perform remedial work. So Halliburton listened to the customer challenges and then developed a new generation of compression set packers known as the OBX Gazlock, which is the tool presented in this slide. The OBX Gazlock is a 10,000 psi bidirectional V0 compression set packer with anchoring capabilities, and it can be used as a standalone packer or with an integral cementer in case multi-stage cement job is required. The OBX Gazlock is an additional barrier to the cement slurry, which helps in preventing sustained casing pressure, especially in high pressure, high temperature wells. As a result of this development, the OBX Gazlock was ran in multiple wells, and the operator reported no sustained casing pressure in these wells. Halliburton recognized the value of using the compression set packers and how these packers are improving the life of the wells to our customer. So Halliburton decided to develop a new design of compression set packers to be utilized with shallower well application. Halliburton designed a new stage cementing tool to meet the customer challenges for less demanding wells, which are losses and fluid flow in some cases. The new stage cementing tool is called the OBX Isolock, which is an extended development of the OBX Gazlock, and it is a compression set packer with an integral cementer. The tool operates regardless of how severe mud loss is in the annulus, which makes the tool highly reliable. The packer is tested as per ISO 14310, and it is V3 6K bidirectional rated. And the tool has 6 dedicated cementing ports, which provides a high flow by area when you compare it to the conventional stage cementing tools. To be specific, it provides more than double the flow by area of the conventional stage cementing tool. This allows the operator also to optimize the second stage cement job displacement rates and as a result to achieve the optimum displacement efficiency. So after the development of the OBX Isolock, Halliburton ran the tool successfully. The packer was set with planned pressure, opened the dedicated cementing ports, performed the second stage cement job with full fluid column, and closed the tool successfully. Also, no sustained casing pressure or leaks were reported by the customer after the job. So lastly, due to the high reliability of these compression set packers and the value added to our customers, Halliburton is leading the industry into upgrading from the conventional inflatable packers toward utilizing the compression set packers and provide our customers with a robust product that extends the life of their wells. Before we wrap this up, I would like to show you Halliburton's OBX family of compression set packers, which consists of 3 tools. The OBX Ecolock, which is an economical, reliable tool and lift cement with an integral stage tool. The OBX Isolock, which I already mentioned, it's a V3 tool, has no slips and lift cement with an integral cementer. And finally, the OBX Gazlock, which is a V0 rated packer, has slips and also can lift cement with a stage cementing tool. These tools are available in various sizes, mainly 13/3/8 and 9 5/8 inch casing. I'd like to thank you all for listening. Please feel free to contact us if you have any questions or if you are interested in any of the presented technologies. Now I'd like to pass this presentation to my colleague, Hector. Thank you all.
Hello, everyone. My name is Hector Ramirez. I'm a cement account representative at the Gulf of Mexico. I will be discussing an LCM application to achieve top cement and minimize the losses during a cement job. We will start off with a little background on the project. This case study is from an operator in the Gulf of Mexico, and then, as you can see, it has a depth of 19,393 feet and TVD of 18,500 feet. This well presented losses through a depleted sand was drilling ahead. The operator decided to run a different variety of conventional LCM concentrations in the mud, not being able to totally stop the losses, but finally reaching TD. The success was marginal though, but the customer decided to proceed to cement with losses. Previous operations with a competitor in nearby offset wells showed around 2,300 barrels losses while drilling down the hole, and then total to severe losses during the cement job, where top cement unfortunately was not achieved. This resulted in more time fixing the issue, pumping an additional liner top-down squeeze job, which meant more money spent by the customer. The solution Halliburton recommended was an LCM package consisting of tune defense LC spacer, adding 10 pounds per barrel of Bridgemaker 2 to the tune defense spacer, and fibers, 1 pound per barrel, added to the tip of the lead slurry. The tune defense spacer LC system is a tailored blend of a polymer, viscosifier, and particles with the addition of proven LCM such as Bridgemaker 2. The well-life 1094 fibers in this lead cement slurry were used to minimize the risk of losses while lifting the cement column throughout the annulus. And finally, a comprehensive engineering tailor approach using a particle wizard software and operational reviews were conducted to select the best LC package option, minimizing the losses in the well-known block. So, due to the severe natural and the costly impact of not reaching the top of cement, we wanted to be as aggressive as possible with this LCM package, but we made sure to perform lab tests with the LCM concentrations chosen to minimize any issue with mixing, pumping LCM in both the spacer and the cement while pumping the cement job. Losses were observed before the tune defense spacer and the lead slurry hit the annulus. Then the losses got minimized until full returns were observed. This was showing a similar to design cement lead pressure curve, as you guys can see in the curve to the right. Is that comparison between design versus real time. There was no need for a remedial cement job covering the oil bearing sand as per plan, resulting in approximately 1,800K savings to the customer. This was very beneficial for the customer. Then the top of cement was verified with LWD, gamma ray, and RA tracer in cement, and the customer was finally able to achieve top of cement successfully as per plan to cover the sand and continue drilling ahead for the next hole section. This additional slide or bone log comparison shows the top of cement with and without the tune defense LCM package. With the LCM package and without it to the right. So in this slide, it can be clearly observed the positive impact that the LCM spacer approach plus the LCM material lead slurry had on achieving the top of cement goal as per plan. Again, your time. Now I will hand it over to the moderators for Q&A.